Welcome to Ultimate Sleep Doctor. Tonight, we journey to realms far beyond our own. Let's consider the grand, silent dance of galaxies stretching across unimaginable distances. These swirling collections of stars, some young and bright, others ancient and fading, represent the very fabric of time and space. It's a humbling thought, isn't it? To realize our planet is just one small piece within this immense, ever-expanding beauty. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe. Let your thoughts drift like clouds across a twilight sky. Let's begin. The very early universe, just a few 100,000 years after the Big Bang, wasn't like the vast, dark expanse we picture today. It was a tremendously dense, hot soup of particles, quarks, leptons, and photons, all jostling and colliding with incredible energy. This initial state, known as the plasma epoch, was so hot that atoms simply couldn't form. The fundamental building blocks of matter were constantly creating and destroying each other in a chaotic dance. But within this primordial soup, something extraordinary was beginning to stir. The seeds of galaxies, and it was a process far more complex and surprising than we initially believed. The prevailing theory for the formation of the first galaxies hinges on the existence of what are called primordial black holes. These weren't born in the violent collisions of stars, as black holes usually are. Instead, they are thought to have emerged in the extreme density fluctuations that arose during the inflationary epoch, that incredibly rapid expansion of the universe in its earliest moments. These fluctuations, tiny variations in the fabric of spacetime itself, acted like gravitational wells, attracting matter with far greater efficiency than gravity alone could manage. As the universe cooled, these gravitational wells became increasingly deep, eventually collapsing under their own weight to form these exotic black holes. Now, the size of these primordial black holes is a fascinating and hotly debated topic. Some models suggest they ranged in mass from tiny, microscopic versions to objects weighing hundreds or even thousands of times the mass of our Sun. Regardless of their exact size, the critical factor was their immense gravitational pull. These black holes, acting as gravitational lenses, began to accumulate surrounding matter, gas, dark matter, and eventually, ordinary hydrogen and helium. This wasn't a gentle process of accretion, where matter spirals slowly towards a central point. Instead, it was a violent, runaway process, driven by the intense gravitational fields of the black holes. Material fell inwards at tremendous speeds, forming dense, swirling disks around the black holes. As matter fell into these disks, it collided with other particles, heating up to incredibly high temperatures. This superheated gas emitted tremendous amounts of ultraviolet light, much more intense than anything we see from distant galaxies today. This early ultraviolet radiation played a crucial role in the next stage of the story, reionization. Before the formation of the first galaxies, the universe was still largely opaque to ultraviolet light. The dense plasma of free electrons constantly scattered photons, preventing them from traveling far. However, The intense radiation from the accreting matter around the primordial black holes began to strip electrons from hydrogen atoms, effectively making the universe transparent to ultraviolet light. This process of stripping electrons is known as reionization. It's a fundamentally transformative event in the history of the universe. As the ultraviolet light from the accreting matter traveled across space, it interacted with the neutral hydrogen, gradually ionizing it, turning it back into a plasma of free electrons and protons. This wasn't a single, instantaneous event. It was a gradual, ongoing process that unfolded over hundreds of millions of years. The intensity of the reionization signal, a specific pattern of ultraviolet light, provides a crucial window into this early epoch. Scientists look for this signal today, trying to detect the first light of the universe. The formation of the first galaxies wasn't solely dependent on these primordial black holes. While the black holes undoubtedly provided the initial gravitational seeds, the surrounding dark matter played a vital supporting role. Dark matter, which constitutes about 85% of the universe's total mass, didn't interact with light, but it did exert gravitational influence. It created even larger gravitational wells, attracting more and more matter to the regions around the black holes and facilitating the growth of these nascent galaxies. The interplay between the black holes, the dark matter, and the surrounding gas created a complex and dynamic environment, constantly evolving and reshaping itself. These early galaxies were vastly different from the spiral and elliptical galaxies we see today. They were smaller, more irregular in shape, and far more intensely luminous. Because of the high radiation environment, they lacked the heavy elements created by stellar nucleosynthesis. The process of creating heavier elements within stars, which is responsible for the beautiful colors and structures of most galaxies. Instead, they were dominated by hydrogen and helium, shining brightly with the ultraviolet light emitted by the accreting matter. These early galaxies weren't just forming, they were actively shaping the evolution of the universe, accelerating the process of reionization and laying the groundwork for the structure we observe today. As reionization progressed, the universe became increasingly transparent, allowing photons to travel across vast distances without being scattered. This, in turn, influenced the growth of these early galaxies, as more photons could penetrate their interiors, stimulating further accretion and luminosity. The process wasn't a perfectly smooth progression. There were periods of rapid reionization followed by pauses as the available gas supply dwindled. The density fluctuations in the early universe, initially seeded by inflation, continued to drive this chaotic growth, creating a tangled web of gravitational forces. The study of the first galaxies and the reionization epoch represents one of the most challenging and exciting frontiers in modern cosmology. While we have made significant progress in understanding the underlying physics, many questions remain unanswered. The precise mass distribution of primordial black holes, the details of the reionization process, and the role of dark matter are still subjects of ongoing research and debate. Ultimately, unraveling the mysteries of this era will provide us with a deeper understanding of the origins of our universe and our place within it. The remnants of this epoch are faintly visible today, imprinted on the cosmic microwave background radiation, the afterglow of the Big Bang. Analyzing the subtle variations in this radiation can provide further clues about the conditions that prevailed during reionization. These faint signals are echoes of a dramatic and transformative period, a time when the universe transitioned from an opaque, hot plasma to the relatively transparent expanse we inhabit now. And as the universe continued to expand and cool, the seeds planted by these primordial black holes and the relentless drive of reionization ultimately led to the formation of the billions of galaxies that now populate the cosmos, a testament to the power of gravity, radiation, and the fundamental laws of physics. The universe, as we've come to understand, isn't just a collection of distant, isolated galaxies. It's a place of immense energy and dramatic events, and at the heart of many of the most spectacular sights we observe are incredibly powerful systems known as active galactic nuclei, or AGN. These aren't simply bright galaxies. They represent some of the most extreme environments in the cosmos, fueled by processes that dwarf almost every other source of energy we encounter. The key to understanding AGN lies in the presence of supermassive black holes at their centers. These black holes aren't your typical stellar remnants, formed from the collapse of massive stars. Instead, they boast masses millions, even billions of times that of our Sun. Their formation, though still not entirely understood, is believed to be intertwined with the evolution of galaxies themselves. One prevailing theory suggests that as galaxies grow and merge, the gravitational interactions lead to the accumulation of vast amounts of gas and dust. This material eventually funnels towards the galactic center, where, under the relentless pull of gravity, it's inevitably drawn into the waiting maw of a supermassive black hole. It's a cosmic feeding frenzy, continuously adding to the black hole's mass. Now, a black hole on its own isn't particularly luminous. It's essentially a region of spacetime where gravity is so intense that nothing, not even light, can escape. However, when a supermassive black hole is actively feeding, it transforms into an AGN, and this is where the truly astonishing phenomena arise. The black hole's immense gravity doesn't just pull in matter, it also traps gas and dust swirling around it, forming a structure called an accretion disk. This accretion disk is a tremendously hot and turbulent region, composed of gas and dust spiraling inward towards the black hole. As the material gets closer, it experiences intense friction and compression, heating up to incredible temperatures, millions of degrees Celsius. This superheated material then emits tremendous amounts of energy across the entire electromagnetic spectrum, from radio waves to X-rays. It's like a giant, cosmic light bulb, only far more complex and dynamic than anything we create on Earth. The emission from the accretion disk is what allows us to detect AGN. The intense radiation is often so bright that it outshines the entire galaxy in which it resides. These bright AGN are sometimes referred to as quasars, a term initially coined for the most luminous of these objects. The term, quasar, originates from the Anglo-Canadian Quasar Survey, a systematic mapping of these distant objects in the early 1960s. It's important to note that while quasar is frequently used to describe the most powerful AGN, the terms are often used interchangeably, though AGN, active galactic nuclei, is a broader term encompassing a wider range of these active systems. The characteristics of an AGN, its brightness, its spectrum, and even its variability, provide crucial information about the properties of the black hole at its center. For example, the speed at which the accretion disk is rotating and the amount of material falling into the black hole can be determined by analyzing the light emitted. These observations provide insights into the black hole's mass, spin, and the dynamics of the surrounding environment. Beyond the accretion disk, AGN often exhibits spectacular outflows and jets. As matter spirals into the black hole, some of it doesn't fall directly in. Instead, it's accelerated outwards along the black hole's rotational axis at speeds approaching a significant fraction of the speed of light. This process is believed to be driven by the black hole's powerful magnetic fields. These fields become twisted and tangled as the material swirls around the black hole, generating intense electric fields that then accelerate the particles. These jets, streams of incredibly energetic particles, can extend for millions of light years, far beyond the host galaxy. They're one of the most puzzling and fascinating aspects of AGN. Scientists are still actively researching the exact mechanisms behind jet formation and acceleration, but it's believed that the magnetic fields play a key role in channeling and collimating the outflowing material. The existence of AGN profoundly affects their host galaxies. The immense energy released by the AGN can heat and ionize the surrounding gas, suppressing star formation in the galaxy. It's a harsh environment, and the galaxy's evolution is significantly influenced by the activity of its central black hole. Furthermore, the energy released by the jets can interact with the surrounding intergalactic medium, creating shock waves and potentially seeding the formation of new star clusters. The study of AGN isn't just about understanding individual systems. It's about understanding the fundamental processes that shape galaxies and the universe itself. By observing these incredibly active systems, we can learn about the conditions that existed in the early universe and the role that black holes played in the formation of the structures we see today. As the universe continues to expand and evolve, AGN remain a vibrant area of research. Astronomers are employing increasingly powerful telescopes, like the James Webb Space Telescope, to probe the faintest and most distant AGN, shedding new light on the evolution of these extraordinary objects and their impact on the cosmic landscape. It's a story still unfolding, a testament to the power and complexity of the universe we inhabit. The universe, as we've explored, is filled with galaxies, enormous islands of stars, gas, and dust held together by gravity. But gravity doesn't just act on galaxies alone. It's a force that, when amplified over immense distances and time scales, builds structures far grander than any single galaxy. These structures are called galaxy clusters, and they represent the largest known gravitationally bound systems in the observable universe. They are, in a sense, the cosmic cities, bustling with activity and harboring some of the most extreme phenomena we study. These clusters aren't simply collections of galaxies bumping into each other. They're held together by a far stronger force: the mutual gravitational attraction between countless galaxies, along with a significant amount of hot, diffuse gas that permeates the entire cluster. This gas, heated to temperatures of tens of millions of degrees Celsius, is incredibly important to understanding cluster formation and evolution. The gas is so hot because it's constantly being compressed and heated by the gravitational interactions of the galaxies within. It's a feedback loop, driven by gravity. The seeds of galaxy clusters begin with smaller, less dense regions of overdensity in the early universe. These slight variations in density, amplified over billions of years, eventually attract more and more matter. Galaxies begin to migrate towards these regions, drawn in by the ever-increasing gravitational pull. As more galaxies join, the density of the core increases, attracting even more galaxies and, crucially, the hot gas that's drawn in alongside them. This process is incredibly complex and doesn't occur in a simple, linear fashion. It's a chaotic dance of attraction and repulsion, a never-ending cascade of gravitational interactions. A typical galaxy cluster contains anywhere from a few hundred to several thousand galaxies. These galaxies aren't all of the same type. You'll find spirals, ellipticals, and irregular galaxies all mixed together, representing a diverse population that has converged over cosmic time. The most massive galaxies, often massive elliptical galaxies, usually dominate the cluster centers. These behemoths exert a significant gravitational influence, pulling in smaller galaxies and shaping the cluster's overall structure. However, the most fascinating part of a galaxy cluster isn't just the galaxies themselves, but the enormous amounts of hot gas that reside within. This gas, known as the intracluster medium, ICM, makes up around 60% of the cluster's total mass. Unlike the cool, dense gas found in spiral galaxies, the ICM is incredibly diffuse and hot. Its temperature is so high that it emits copious amounts of X-rays. Astronomers detect this X-ray emission using specialized telescopes designed to observe these wavelengths. Analyzing the X-ray spectrum of the ICM gives us a direct measure of the gas's temperature and density, essential information for understanding the cluster's dynamics. The ICM isn't static. It flows and swirls around the galaxies within the cluster. This flow is driven by the cluster's overall gravitational potential and influenced by the motions of the galaxies. Sometimes, the ICM forms beautiful filamentary structures resembling wisps of smoke, called filaments. These filaments represent regions of lower density where gas is gradually being drawn into the cluster. Conversely, there are also voids, vast, empty spaces between clusters where the density of matter is extremely low. These voids reflect the overall large-scale structure of the universe, which is characterized by a cosmic web, with dense filaments and clusters interspersed with empty regions. Galaxy clusters are also the sites of some of the most energetic events in the universe, the mergers of galaxy clusters. When two clusters collide, the interaction is profoundly violent. The hot gas in each cluster is compressed, heating up and accelerating outwards in powerful shocks. These shocks generate tremendous amounts of energy, which can be released in the form of radio waves, X-rays, and gamma rays. These mergers are incredibly dynamic and disrupt the structures of both clusters, often leading to the formation of a new, more massive cluster. The process is not just about adding galaxies together, but fundamentally altering the very fabric of the cluster. Furthermore, galaxy clusters play a vital role in the formation and evolution of galaxies themselves. The gravitational influence of the cluster can strip gas from smaller galaxies, effectively quenching their star formation. This feedback mechanism is crucial. Otherwise, smaller galaxies would simply keep accumulating gas and become increasingly bright and massive. The cluster's gravity acts as a regulator, preventing the runaway growth of individual galaxies. Studying galaxy clusters allows us to probe dark matter, the mysterious substance that makes up about 85% of the universe's mass. Because dark matter doesn't interact with light, it's invisible to telescopes. However, its gravitational effects are observable through its influence on the motion of galaxies within the cluster and the distribution of the hot gas in the ICM. Analyzing the mass distribution within a cluster provides a powerful way to map the distribution of dark matter. The Hercules cluster, located in the constellation Hercules, is a particularly rich and well-studied cluster. It is one of the brightest clusters of galaxies visible from Earth and provides an exceptional laboratory for observing and understanding these complex systems. Scientists use it to study the properties of the ICM, map the distribution of dark matter, and observe the effects of mergers and shocks. Similarly, the Coma cluster is a popular target for research, offering a different perspective on the dynamics and evolution of galaxy clusters. Ongoing research into galaxy clusters continues to refine our understanding of the universe's structure, the nature of dark matter, and the processes that govern the formation and evolution of galaxies. Each observation, each measurement, brings us closer to unraveling the secrets held within these grand, gravitationally bound systems. They truly are the largest, most complex structures in the cosmos, a testament to the power of gravity and the beauty of the universe's intricate design. The universe, as we've begun to understand it, isn't quite the beautiful, sparkling vista of swirling galaxies we see in photographs. It's a much more complex and, frankly, stranger place than we initially perceived. The galaxies themselves, those magnificent pinwheels of stars, are just the visible tip of a vast, unseen iceberg. Beneath the luminous surface of the cosmos lies a scaffolding, a framework built not of atoms or light, but of something far more elusive, dark matter. For decades, astronomers observed a puzzling anomaly. Galaxies were rotating far too quickly. Based on the amount of visible matter, the stars, gas, and dust, they should have flung themselves apart. The gravitational pull of the stars within a galaxy simply wasn't strong enough to hold everything together at the speeds that observations revealed. It was like watching a merry-go-round spinning at an impossible speed, defying the laws of physics as they were understood. Something was providing the extra gravitational grip, and this became known as the missing mass problem. The solution, eventually, came in the form of the concept of dark matter halos. These halos aren't made of the same stuff as the stars and planets we know. They don't interact with light in any significant way, which is why we can't directly observe them. Instead, they are vast, extended regions of space containing a form of matter that interacts through gravity, much like ordinary matter, but far more weakly. Scientists theorize that these halos existed around galaxies and around galaxy clusters as well, acting as immense gravitational wells. The idea wasn't born out of thin air. The first serious consideration of dark matter as a gravitational component came from Fritz Zwicky in the 1930s while studying the Coma cluster of galaxies. Zwicky noticed that the velocities of the galaxies within the cluster were far higher than what could be accounted for by the visible mass. He estimated the cluster's mass based on its gravitational influence, and he found a staggering difference, a discrepancy of roughly 100 times the visible mass. He dubbed this dark matter, and his initial calculations were remarkably accurate. Now imagine a galaxy as a delicate flower, a beautiful blossom of stars. The visible matter, the stars, the gas, the dust, forms the petals and the central core of the flower. But what holds the flower together? What provides the support, the underlying structure? The dark matter halo is that structure. It's a sphere of invisible matter that extends far beyond the visible boundaries of the galaxy. It's like a gigantic, ghostly bubble encompassing the galaxy, its gravity subtly pulling everything inwards. The size of these dark matter halos varies considerably. Smaller galaxies tend to have smaller halos, while larger galaxies, like our own Milky Way, reside within enormous halos that span hundreds of thousands of light years. These halos aren't uniform. They're denser in some regions and sparser in others. The density profiles, or the way the dark matter is distributed within the halo, are still actively being researched and refined. Scientists use sophisticated computer simulations to model the formation and evolution of these halos. The formation of dark matter halos is intimately linked to the very early universe. In the incredibly dense and chaotic conditions immediately following the Big Bang, tiny fluctuations in the density of the universe began to grow. These fluctuations, amplified by gravity, eventually led to the collapse of regions of space, forming the seeds for dark matter halos. As these halos grew, they attracted surrounding gas, which then cooled and condensed, eventually giving rise to the first stars and galaxies within them. The dark matter halo provided the gravitational scaffolding for this process. It's important to remember that dark matter is just stuff floating around. It actively participates in the universe's evolution. Its gravity dictates how galaxies form, how they interact with each other, and even how they influence the large-scale structure of the cosmos. Without dark matter, the universe would be a far more desolate and uniform place. Galaxies wouldn't have been able to coalesce and create the intricate web of structures we observe today. Current estimates suggest that dark matter makes up approximately 85% of the matter in the universe. Ordinary matter, the the stuff we're made of accounts for only about 15%. This dramatically shifts our understanding of the cosmos. It highlights just how much of the universe remains hidden, a silent, unseen force shaping everything we can observe. Scientists are using increasingly powerful telescopes, like the James Webb Space Telescope, to probe deeper into the universe, hoping to gain further insights into the nature of dark matter and the intricate dance of its gravitational influence. The ongoing research into dark matter halos is a testament to the remarkable progress in our understanding of the universe. It's a reminder that the cosmos is full of surprises and that there are still countless mysteries waiting to be unveiled. As we continue to explore, we're not just learning about the distribution of matter in the universe, but also about the fundamental laws that govern its evolution. It's a truly humbling and fascinating endeavor. The universe, as we've begun to understand, isn't a static collection of islands. It's a place of constant, dramatic interaction. Galaxies, those magnificent spirals and ellipticals, aren't simply drifting through space. They're engaging in a slow, powerful dance of collision and transformation. At the heart of this dance are galaxy mergers, some of the most breathtaking and fundamental processes shaping the cosmos. These events aren't gentle encounters. They're spectacular gravitational ballets, driven by the irresistible pull of gravity, and they are responsible for much of the star formation and morphological evolution we observe across cosmic time. Consider a pair of galaxies, initially quite separate, each containing billions of stars, gas, and dust. Both are rotating, driven by the gravitational forces within their own individual structures. As they approach each other, a remarkable thing begins to happen. The galaxies start to tug on each other, a subtle dance initially, but with increasing intensity as they get closer. This tugging isn't just a gentle nudge, it's a profound distortion of space-time itself. The gravitational fields of the galaxies warp the fabric of the universe around them, and this distortion becomes stronger and stronger as they draw nearer. This process isn't linear, it's chaotic and complex. The galaxies don't simply smash together head-on, though sometimes that happens, particularly in smaller mergers. Instead, the gravitational forces cause the stars within each galaxy to experience tremendous accelerations. They are flung outwards, stretched and distorted as they try to escape the intense pull. But the gravitational forces remain, relentlessly drawing the galaxies closer. The stars themselves, despite their immense distances, are affected, momentarily curving their paths as they pass through the warped space. As the galaxies get closer, tidal forces, the stretching of matter by gravity, become dominant. These forces create vast, diffuse structures known as tidal tails. These aren't just wispy streams of gas and dust. They're incredibly complex and beautiful. They represent the material ripped away from the galaxies as they're distorted and pulled apart. The tails stretch out for millions of light years, remnants of the galaxy's former shapes. But the real magic of galaxy mergers lies in what happens to the gas and dust that's brought together. Initially, this material is spread out, creating a diffuse, hot gas cloud. However, the immense gravitational forces compress this cloud, heating it up to incredible temperatures, millions of degrees Kelvin. This superheated gas then begins to collapse under its own weight, triggering an astonishing burst of star formation. This isn't a slow, gradual process. It's a runaway reaction, with vast clouds of gas collapsing and igniting countless new stars. The newly formed stars are often massive and luminous, what astronomers call population II stars, because they're born from the densest regions of the compressed gas. These massive stars burn their fuel incredibly quickly, living short but brilliant lives. As they die, they explode as supernovae, scattering heavy elements, the building blocks of planets and life, back into the surrounding gas. This feedback from supernovae is crucial, enriching the gas with the materials needed to create the next generation of stars and planets. The shape of the resulting galaxy is dramatically altered. Before the merger, the galaxies might have been spiral, with beautiful, swirling arms. After the merger, they often transform into an elliptical galaxy, a smooth, featureless shape with a more uniform distribution of stars. This is because the intense star formation and subsequent mergers have smoothed out the existing structures. The swirling arms are disrupted, and the galaxies become more spherical as stars are flung into new orbits. Not all mergers are symmetrical. Sometimes, one galaxy is significantly larger and more massive than the other. In these cases, the smaller galaxy is completely disrupted and consumed by the larger one, leaving behind a distorted remnant. These mergers can create incredibly complex structures with multiple rings and tidal features. The rate at which galaxy mergers occur has also changed over cosmic time. In the early universe, when the density of matter was much higher, mergers were much more frequent. As the universe expanded and matter became more diffuse, the rate of mergers slowed down. However, mergers are still ongoing today, although they are less frequent and less dramatic than in the early universe. The Milky Way, our own galaxy, is currently on a collision course with the Andromeda Galaxy, a grand merger that is expected to occur in about 4.5 billion years. Understanding galaxy mergers is fundamental to understanding the evolution of galaxies and the distribution of matter in the universe. They are a powerful engine for star formation and a key driver of morphological change, creating some of the most stunning and complex structures in the cosmos. They are a reminder that the universe is not a static place, but a dynamic and ever-changing one, sculpted by the relentless forces of gravity. The Milky Way, our home galaxy, isn't just a solitary island in the vast darkness. It's constantly interacting, constantly being shaped by the gravitational dance of countless other galaxies. And sometimes, those interactions leave behind faint, shimmering traces, what astronomers call stellar streams. These aren't streams of water, of course, but rather rivers of stars, remnants of galaxies that have been torn apart and absorbed by our own. They represent some of the most beautiful and poignant evidence of the universe's constant cycle of creation and destruction. These stellar streams are formed through a process known as tidal disruption. When two galaxies get close enough, often in the course of a larger merger or a gravitational encounter, their gravitational fields begin to pull on each other. The stars, being much less massive and slower to respond, are the first to feel the strain. They're stretched and distorted, their orbits elongated, until they're effectively ripped from their original galaxy. These detached stars then continue to orbit the Milky Way, following paths dictated by our galaxy's own gravity. It's like a cosmic game of bumper cars, but instead of metal and collisions, it's stars swirling around each other. The density of the stream, how closely packed the stars are, gives astronomers clues about the original galaxy that formed it. Thicker, more tightly wound streams generally indicate that the original galaxy was more massive and had a stronger gravitational pull. These denser streams are often easier to detect. Conversely, thinner, more diffuse streams might be remnants of smaller, fainter galaxies. One of the most prominent stellar streams currently orbiting the Milky Way is called the Monoceros Ring. This particular stream originates from a dwarf galaxy called NGS-1, located in the direction of the constellation Monoceros. NGS-1 was essentially cannibalized by the Milky Way billions of years ago. As it approached, our galaxy's gravity started pulling at its stars, gradually stretching them into this elongated band of light. The stars within the Monoceros Ring aren't just scattered randomly. They follow a remarkably curved path around the Milky Way, reflecting the original galaxy's orbital motion before it was disrupted. Analyzing the star's chemical composition, the abundance of elements like hydrogen and helium offers another vital piece of information. The stars within the Monoceros Ring closely resemble stars found in the local group, the cluster of galaxies that includes the Milky Way and Andromeda, suggesting that the disrupted galaxy was once part of a similar environment. Beyond the Monoceros Ring, astronomers have identified dozens of other stellar streams, each with its own unique characteristics and origins. The Gaia mission, a European Space Agency satellite, has been particularly instrumental in discovering and studying these streams. Gaia's extremely precise measurements of the positions and motions of billions of stars allow astronomers to map these streams with unprecedented detail. These streams aren't just pretty patterns in the sky, they're invaluable archives of the early universe. They provide a glimpse into the conditions and processes that shaped the first galaxies. Scientists are particularly interested in streams originating from galaxies that existed much earlier in the universe's history. These ancient streams can offer clues about the formation of the very first galaxies, the behemoths that seeded the cosmos, with the building blocks of stars and planets. The further back in time we look, the more difficult it becomes to study these streams, as they become increasingly faint and distorted. However, with advancements in technology and ongoing surveys like Gaia, astronomers are continually refining their understanding of these faint, distant echoes. Another fascinating aspect of stellar streams is their interaction with the interstellar medium, the gas and dust that fills the space between stars within the Milky Way. As these streams pass through regions of denser gas and dust, the stars within them experience additional tidal forces, further disrupting their orbits and altering their properties. This interaction can lead to the formation of stellar clusters, small groups of stars born from the same cloud of gas and dust. These clusters are often found along the paths of stellar streams, providing further evidence of their origin. The study of stellar streams is a surprisingly complex undertaking. Astronomers use sophisticated computer simulations to model the gravitational interactions between galaxies and their surrounding environment. These simulations help them to understand how stellar streams are formed, how they evolve, and how they interact with the interstellar medium. But observations remain crucial. Analyzing the light from these streams, identifying individual stars, and measuring their velocities provides the ground truth against which the simulations can be tested and refined. Furthermore, astronomers are now employing new techniques like gravitational microlensing to study stellar streams that are too faint to be observed directly. Microlensing occurs when a massive object, such as a foreground star, passes in front of a more distant star, temporarily magnifying its light. By analyzing the changes in brightness, astronomers can detect the presence of stars within a faint stellar stream. The ongoing exploration of stellar streams is pushing the boundaries of our understanding of galaxy evolution and the formation of the large-scale structure of the universe. These shimmering trails of lost galaxies are not just beautiful curiosities. They are vital tools for unraveling the mysteries of our cosmic neighborhood. They represent the quiet, persistent testimony of countless cosmic collisions, shaping the galaxies we see today. As we continue to observe and study these streams, we are, in essence, tracing the footsteps of the universe itself. The universe, as we've been discovering, isn't just a vast, empty space filled with countless individual stars. It's organized, surprisingly so, into structures of immense scale. We've seen how dark matter halos, the invisible anchors of galaxy formation, dictate where galaxies cluster and how they grow. We've witnessed the dramatic processes of galaxy mergers, transforming sleepy spirals into chaotic, bright behemoths, and observed the delicate trails, stellar streams, left behind by galaxies that have been ripped apart in gravitational dances. But understanding the sheer number of galaxies, billions upon billions scattered across the observable universe, presented a problem. How could astronomers possibly keep track of them? How could they begin to understand their relationships and their evolution? The answer, developed largely thanks to the work of Edwin Hubble, lies in a system called the Hubble sequence. The Hubble sequence is essentially a chart, a kind of family tree for galaxies. It classifies galaxies based primarily on their shape, their visual appearance. Hubble, in the early 20th century, meticulously studied the spectra of light emitted by these distant galaxies, analyzing the patterns of absorption lines to determine their velocities and distances. He noticed a remarkable trend, that galaxies could be broadly grouped into three main categories: elliptical, spiral, and irregular. These weren't just arbitrary groupings. They were linked to something fundamental, the way these galaxies were evolving over time. Let's begin with the most common type, the ellipticals. These galaxies are typically smooth and featureless, appearing as blurred, oval shapes. They lack the distinct spiral arms or bright central disks seen in spirals. Their light is remarkably uniform in all directions, as if the stars within them are randomly distributed. Astronomers believe that ellipticals often form through the violent merger of spiral galaxies, a process that strips away their intricate structures, leaving behind a more disordered, spherical distribution of stars. They tend to be older, containing a high proportion of older, redder stars because star formation has largely ceased within them. They are often found in the centers of galaxy clusters, where their gravitational pull is strong enough to halt further star formation in smaller galaxies that might otherwise be forming new stars. Then there are the spirals, the most familiar and perhaps the most visually striking type of galaxy. Spirals are characterized by a central, flattened disk containing billions of stars and prominent, swirling arms that extend outwards from the center. These arms aren't static structures. They're regions of intense star formation, where gas and dust are compressed and ignited by the gravity of the galaxy. The spiral arms aren't made of simply stars. They're regions filled with young, blue stars, hotter and brighter than the older stars found in the galactic core. The Hubble sequence distinguishes between two main types of spiral galaxies: normal spirals and barred spirals. Normal spirals have a central bulge and spiral arms radiating outwards. Barred spirals, as their name suggests, have a bar-shaped structure running through their center, with the spiral arms emanating from the ends of the bar. The presence of the bar significantly affects the galaxy's dynamics, often funneling gas towards the center, stimulating bursts of star formation. Finally, we have the irregulars. These galaxies don't fit neatly into either the elliptical or spiral categories. They often have chaotic, asymmetrical shapes, with no distinct spiral arms or central bulge. They are frequently the result of gravitational interactions with other galaxies, perhaps a close encounter that disrupted their structure, or a collision that simply couldn't be resolved into a regular shape. Irregulars are typically sites of active star formation, with large clouds of gas and dust fueling the birth of new stars. They represent the most dynamic and unpredictable stage of galactic evolution, constantly changing and evolving under the influence of their environment. It's important to recognize that the Hubble sequence isn't a rigid, unchanging system. It represents a snapshot in time. Galaxies aren't static. They're constantly evolving. Over billions of years, galaxies can change their type. A spiral galaxy, for example, can evolve into an elliptical galaxy through repeated mergers. The Hubble sequence provides a framework for understanding the typical progression of galactic evolution, but it's just one piece of the puzzle. The detailed study of galaxy morphology, the study of their shapes, combined with observations of their stellar populations, gas content, and star formation rates, allows astronomers to piece together the complex story of how galaxies came to be and how they continue to transform over cosmic timescales. Furthermore, recent observations, particularly from telescopes like the Hubble Space Telescope and the James Webb Space Telescope, have revealed a much more nuanced picture than Hubble initially envisioned. We've discovered galaxies that seem to defy categorization, displaying features of multiple types, suggesting that the process of galactic evolution is far more complicated and continuous than the simple sequence implied by the Hubble sequence. but the sequence remains a vital cornerstone of our understanding, providing a fundamental framework for classifying and studying these magnificent cosmic islands, and continues to be refined and expanded as our knowledge of the universe grows. The universe, as we've come to understand, doesn't simply create stars. It also has a rather beautiful and poignant way of bringing them to an end. Long before a star explodes in a spectacular supernova, a truly awe-inspiring event, there's a gentler, more delicate phase of its life, and this phase culminates in what we call a planetary nebula. These aren't actually planets, you see. The name comes from early astronomers who, through their telescopes, observed these glowing shells and mistakenly thought they resembled the distant worlds of our solar system. But planetary nebulae are far more complex and significant than simple misinterpretations. They represent the final act of transformation for stars like our own sun, stars that have spent their lives fusing hydrogen into helium within their cores. As a star exhausts the hydrogen fuel in its core, it begins to contract. This contraction isn't sudden and violent. It's a slow, steady process driven by the relentless pull of gravity. As the core shrinks, the temperature and pressure increase dramatically. Eventually, the core becomes hot enough to begin fusing helium into heavier elements, such as carbon and oxygen. This helium burning phase is shorter and more intense than the hydrogen burning phase. However, these low-mass stars, those with masses similar to or less than our sun, don't become massive enough to ignite heavier elements like neon, magnesium, or silicon in their cores. They simply run out of fuel. With no more fusion happening in the core, the outward pressure generated by the energy released during nuclear reaction ceases. Gravity, unchecked, takes over. The star's core begins to collapse inward, shrinking rapidly. This collapse doesn't immediately destroy the entire star. Instead, the outer layers of the star, now loosely held together by radiation pressure from the core, are dramatically expelled into space. This outward flow of material creates a huge, expanding bubble, the precursor to the planetary nebula. The rate at which the material is ejected is incredibly high. It's like a fountain of gas and dust shooting outwards at speeds reaching tens of thousands of kilometers per second. The expelled gas isn't uniform. It's composed of several distinct layers, each with different temperatures and densities. The innermost layers closest to the former star's core are often intensely hot, glowing with the ultraviolet radiation produced by the core's residual heat. These are the hottest, brightest parts of the nebula. As you move further outwards, the temperature gradually decreases, and the gas becomes cooler and dimmer. The outer layers are often ionized by the ultraviolet light from the core, causing them to shine with vibrant colors, blues, greens, and reds, created by the excitation of specific elements within the gas. The exact colors depend on the elements present and how strongly they're ionized. During this ejection process, the core of the star, now devoid of its outer layers, becomes a white dwarf. A white dwarf is an incredibly dense remnant, composed primarily of carbon and oxygen. It's supported against gravity by a process called electron degeneracy pressure, a quantum mechanical effect that prevents the electrons from being squeezed too closely together. White dwarfs don't produce any energy through nuclear fusion. They simply cool down and fade over billions of years. The expanding shell of gas surrounding the white dwarf, the planetary nebula, can expand to enormous distances, sometimes hundreds of light years across. These nebulae aren't static entities. They are constantly evolving as the remaining gas interacts with the surrounding interstellar medium, the space between stars. The shock waves generated by the expanding nebula compress and heat the surrounding gas, triggering further ionization and causing the nebula to change shape, sometimes dramatically. The beautiful, intricate structures we often see in planetary nebulae, the delicate filaments, the bright knots, the intricate patterns, are all the result of this dynamic interaction. Scientists study planetary nebulae to learn about the composition and evolution of stars. By analyzing the spectral lines, patterns of light emitted by different elements, in the light from a planetary nebula, they can determine the types of elements present in the star's atmosphere and core. This information provides valuable clues about the star's history and its eventual fate. It's like reading a cosmic fingerprint, revealing the story of a star's life. Many planetary nebulae have complex, symmetrical shapes, often resembling rings, spirals, or hourglasses. The origin of these shapes is still being actively researched, but it's believed that they are influenced by the star's rotation and magnetic field. The interaction with the interstellar medium also plays a significant role, creating asymmetries that eventually become visible in the nebula's structure. Some planetary nebulae are even found in binary systems, where the interaction between the two stars further complicates the process. Eventually, after hundreds of thousands to tens of millions of years, the gas in the planetary nebula disperses into the interstellar medium. The white dwarf that remains slowly cools and fades, becoming a cold, dark remnant, a black dwarf, though the universe isn't old enough for any black dwarfs to have formed yet. The material ejected from the planetary nebula enriches the interstellar medium with heavier elements, elements that were created during the star's life and now become the building blocks for future generations of stars and planetary systems. So, in a way, the death of a star contributes to the creation of new worlds. It's a truly beautiful and fundamental cycle of cosmic transformation. The universe, as we've begun to understand, isn't just a collection of swirling galaxies, beautiful as they may be. It's a dynamic, evolving place, full of processes operating on scales beyond our everyday experience. One of the most fascinating of these processes, and crucially important for understanding the grand scale of the cosmos, is the explosive death of a star, specifically, a type known as a supernova type Ia. These aren't like the dramatic, red giant endings of massive stars. Instead, they represent a remarkably consistent and predictable event, offering astronomers a tool unlike any other for measuring distances across vast stretches of space. Supernova-type Ia events originate from a specific kind of binary star system. Within this system, one star is a white dwarf, the dense, remnant core of a once massive star that has exhausted its nuclear fuel. The other star in the system might be a main sequence star, a red giant, or even another white dwarf. What's particularly important is that the white dwarf isn't capable of further nuclear fusion. It's incredibly compact, packing the mass of the Sun into a sphere roughly the size of our planet. As it accumulates matter from its companion star through a process called accretion, it steadily approaches a critical limit, a point known as the Chandrasekhar limit. This limit, roughly 1.4 times the mass of our Sun, is where the physics becomes unstable. Once the white dwarf surpasses this limit, a runaway nuclear fusion reaction begins in its core. Unlike the slower, more controlled fusion that occurs in main-sequence stars, the fusion in a Type Ia supernova is incredibly rapid and violent. It begins with carbon fusion, then quickly ignites oxygen, neon, magnesium, silicon, and finally, iron. This isn't a gradual process. It's an instantaneous chain reaction, converting core material into energy at an astonishing rate. The entire core collapses in on itself in a fraction of a second, followed by a rebound, a powerful shockwave that propagates outward through the star. This shockwave tears the star apart in a spectacular explosion, releasing an enormous amount of energy, typically 100 to 400 times more energy than our Sun will ever produce in its entire lifetime. What makes supernova Type Ia so special and so valuable is the consistency of their brightness. Unlike other supernovae, which vary greatly in their luminosity due to differences in the mass of the progenitor star, Type Ia supernovae always reach a remarkably similar peak brightness. This consistency is because the explosion itself is governed by a precise physical mechanism, the thermonuclear runaway of carbon and oxygen in the white dwarf. The peak luminosity is remarkably predictable, meaning that if we can determine the brightness of a Type Ia supernova as seen from Earth, we can then use that information to calculate its distance. This process is called standard candle astronomy. Think of it like this. We know that a flashlight always produces a certain amount of light. If we measure how bright that flashlight appears to us from a distance, we can use that information to calculate how far away it is. Supernova Type Ia supernovae behave in a similar way. They're essentially standard candles with a fixed luminosity. Astronomers observe the brightness of a Type Ia supernova as it fades over time. By plotting the brightness against the time since the explosion, they create a light curve. The shape of this light curve is what allows them to determine the distance to the supernova. The technique relies on a fundamental relationship in the universe, discovered by Edwin Hubble and others, that redshift is directly proportional to distance. Redshift describes the stretching of light waves as an object moves away from us. The more redshifted the light, the faster the object is receding, and the farther away it is. However, knowing the distance to a Type Ia supernova isn't just about redshift. It's about using the supernova's known intrinsic brightness, its peak luminosity, to cross-calibrate the cosmic distance ladder. The cosmic distance ladder is a series of techniques, each calibrated using the previous one, that allow astronomers to measure distances to increasingly distant objects. The farthest distances are measured using the cosmic microwave background, the afterglow of the Big Bang. Type Ia supernovae are crucial stepping stones in this ladder, acting as a tool to calibrate other distance indicators, such as Cepheid variable stars and type II supernovae. By accurately determining the distance to a few nearby type Ia supernovae, astronomers can then use those measurements to calibrate the distances to more distant objects, ultimately enabling them to map the large-scale structure of the universe. The discovery of type Ia supernovae as standard candles revolutionized our understanding of the cosmos. They provided the first compelling evidence for the accelerating expansion of the universe, a discovery that led to the concept of dark energy, a mysterious force driving this acceleration. Studying these exploding stars continues to be a vital component of modern cosmology, helping us to unravel the secrets of the universe's past, present, and future. The predictable nature of their demise, transforming them into brilliant beacons, continues to guide us across the immense gulfs of space and time. The universe, as we've come to understand it, is a place of constant, breathtaking transformation. Stars are born, they burn brightly, and eventually they fade away, leaving behind remnants that continue to shape the cosmos. We've discussed the intricate dance of galaxies, the stories whispered by dying stars, and the surprisingly reliable methods we've developed for measuring distances across vast stretches of space. But even within these established processes, there exist phenomena so extraordinarily powerful, so utterly sudden and violent, that they challenge our comprehension of energy and physics itself. These events are known as gamma-ray bursts, and they represent the most energetic explosions observed in the observable universe. Gamma-ray bursts are not like supernovae, although they share a common origin. While supernovae involve the collapse of a massive star's core, releasing tremendous energy over days or weeks, GRBs are far more concentrated and incredibly brief. They are fleeting flashes of gamma radiation, the highest energy form of electromagnetic radiation, lasting anywhere from milliseconds to a few seconds. What makes them so special is the sheer amount of energy released in a tiny volume of space, often more than the sun will emit in its entire lifetime. The bursts are initially detected by specialized satellites, instruments that are specifically designed to scan the universe for these intense bursts of radiation. These satellites, like the SWIFT mission and the Fermi Gamma Ray Space Telescope, essentially act as cosmic Geiger counters, amplifying the faint gamma rays and relaying the information back to Earth. The source of these events remains an area of intense research, but the prevailing theory centers around the formation of stellar corpses, specifically rapidly rotating, extremely dense neutron stars known as magnetars. Magnetars possess extraordinarily powerful magnetic fields, billions of times stronger than any magnetic field we experience on Earth. The leading hypothesis, dubbed the collapsar model, proposes that when a massive star, significantly larger than our Sun, but not massive enough to undergo a traditional supernova, undergoes a core collapse, the resulting neutron star rapidly spins, and its powerful magnetic field becomes twisted and strained. This strain isn't sustained. Instead, it leads to a catastrophic event. The magnetic field, under immense pressure, abruptly rips through the star's crust, creating a channel that plunges deep into the newly formed neutron star. This process is akin to pulling a plug from a dam, except the plug is a magnetic field and the dam is the star's own structure. The immense energy released during this sudden disruption is what fuels the burst. It's not just a collapse, it's a violent, shearing disruption of the star's internal structure. However, the exact mechanisms are still debated. There's a possibility that a small, rapidly rotating black hole forms alongside the neutron star, and it's this nascent black hole that's responsible for the burst. Alternatively, the energy release might be primarily due to the magnetic field itself, twisting and accelerating charged particles to near the speed of light before they are abruptly halted, releasing their accumulated energy in the form of gamma rays. It's plausible that both processes contribute, creating a complex and chaotic interaction at the heart of the burst. The initial burst of gamma radiation is incredibly dangerous, ionizing the surrounding interstellar medium, stripping electrons from atoms, and creating a firewall of high-energy particles. This firewall expands outwards at nearly the speed of light, creating a shockwave that can significantly impact the surrounding environment. What's fascinating is that these bursts aren't always accompanied by visible light. Many GRBs are detected primarily through their afterglow, a gradual fading of lower energy radiation, such as X-rays, optical light, and even radio waves, that extends for days, weeks, or even months after the initial burst. The afterglow provides invaluable information about the burst's distance and the environment in which it occurred. By analyzing the spectrum of light from the afterglow, astronomers can determine the composition of the surrounding gas and dust, allowing them to estimate the distance to the burst. This is incredibly important because GRBs are incredibly distant, often located hundreds of millions of light years away. Their extreme distances make it difficult to study them in detail, but the afterglows are essentially their fingerprints, allowing us to measure their properties and learn about the universe's most energetic events. Furthermore, GRBs aren't just cosmic fireworks. They also play a role in galaxy evolution. The powerful shockwaves generated by these bursts can trigger star formation in the surrounding gas clouds. The energy input can compress the gas, initiating the process of star formation, effectively seeding new galaxies with the building blocks for future generations of stars. It's a violent, transformative process, shaping the landscapes of galaxies across cosmic distances. Despite their brief existence, gamma-ray bursts leave a lasting impact on the universe, acting as catalysts for change and contributing to the ongoing story of cosmic evolution. Ongoing research and new observations continue to refine our understanding of these incredible events, promising even more surprises in the years to come. The night sky, as we've explored it across countless light years, isn't a static, unchanging backdrop. It's a dynamic, evolving painting, constantly shifting and expanding. The observations made with telescopes like Hubble and even more recently with the James Webb Space Telescope revealed a truly astonishing fact. Galaxies aren't just randomly scattered across the cosmos. They are moving away from us, and crucially, the further away they are, the faster they're moving. This wasn't something scientists simply guessed. It was a conclusion drawn from meticulous measurements of distances and velocities. The key to understanding this dramatic movement lies in a remarkable relationship first observed by Edwin Hubble in the late 1920s. Hubble was studying the spectra of light emitted by distant spiral galaxies. Spectra are like fingerprints of light. They reveal the specific wavelengths that are absorbed or emitted by an object. Analyzing these spectral lines allowed Hubble to determine the elements present in the gas within those galaxies, and more importantly, to measure the velocity at which these galaxies were moving towards or away from Earth. He noticed a consistent pattern. The spectral lines weren't just shifted, they were systematically redshifted. Redshift is the stretching of light waves as an object moves away from its observer. Think of it like the sound of a siren. As an ambulance speeds away, the pitch of the siren decreases, becoming lower and lower until it's beyond the range of human hearing. Similarly, light waves are stretched as they travel through an expanding space, shifting towards the red end of the spectrum. The amount of redshift directly corresponds to the galaxy's velocity. The greater the redshift, the faster the galaxy was receding. Hubble plotted these velocities against the distances to the galaxies. He painstakingly measured the distances, initially using Cepheid variable stars as standard candles, allowing for distance estimations, and then correlated them with the observed redshifts. What he found was a remarkably linear relationship. This means that for every distance, there was a corresponding velocity, and vice versa. He formulated an equation that beautifully described this relationship. V equals h0d, where v represents the velocity of a galaxy. h0 is a constant known as the Hubble constant, and d is the distance to the galaxy. The Hubble constant represents the rate at which the universe is expanding at a given distance. It's a fundamental parameter in cosmology, a way of quantifying the universe's expansion. However, determining the exact value of h0 has been a surprisingly challenging endeavor. Early measurements yielded different results, leading to what became known as the Hubble tension. Modern measurements using different techniques, such as the cosmic microwave background radiation and type Ia supernovae, continue to generate slightly varying values for the Hubble constant, creating a discrepancy that scientists are still actively investigating. This discrepancy could point to new physics beyond our current understanding of the universe. The expansion of the universe isn't like an explosion in the traditional sense. It's not that galaxies are flying away from a central point. Instead, space itself is expanding, carrying the galaxies along with it. It's as if the fabric of space-time is stretching, creating more room for the galaxies to move into. Imagine a loaf of raisin bread dough rising. As the dough expands, the raisins, representing galaxies, move further apart from each other, not because they're actively moving through the dough, but because the dough itself is growing. This expansion has been unfolding since the Big Bang, the event that marks the beginning of the universe approximately 13.8 billion years ago. The Big Bang wasn't an explosion in space. It was an expansion of space itself. At the very beginning, the universe was incredibly hot and dense, and everything was compressed into a tiny single point. As the universe expanded, it cooled, allowing for the formation of subatomic particles, then atoms, then eventually galaxies and stars. The expansion rate has also changed over time. In the early universe, the expansion was accelerating, driven by a mysterious force called dark energy. As the universe continues to expand, this acceleration is expected to continue, leading to a future where galaxies are increasingly isolated from one another. Eventually, the observable universe will become dominated by galaxies so distant that their light will never reach us. The Hubble law and the expansion of the universe it describes isn't just a theoretical concept. It's a cornerstone of modern cosmology. It provides a framework for understanding the origin and evolution of the universe. It allows us to estimate the age of the universe, to study the large-scale structure of the cosmos, and to probe the fundamental nature of space and time. Furthermore, the ongoing investigation into the Hubble tension, the disagreement between different measurements of the Hubble constant, is driving innovation and research within the field of cosmology. It's forcing scientists to reconsider our understanding of dark energy, dark matter, and the very nature of the universe. As we continue to explore the depths of space with powerful telescopes and sophisticated instruments, we're continually refining our knowledge of this expansion and the forces that govern it. The night sky, once a static backdrop, is revealed to be a dynamic, expanding entity, a story of creation and evolution that unfolds before our very eyes. And just as the universe is expanding, so too is our understanding of it, a process of continual discovery and revelation, inviting us to contemplate our place in the grand scheme of things. The universe, as we've come to understand it, wasn't always the vast, complex place it is today. It began in a fraction of a second with an event so intense, so fundamentally altering, that it's still echoing across space and time. That beginning is what cosmologists call the Big Bang. And while we can't directly see the moment of the Big Bang itself, it's, by definition, the beginning, we've discovered a remarkable way to study it, a kind of ghostly imprint left behind. This imprint is known as the cosmic microwave background radiation, or CMB for short. For countless years, scientists observed a faint, uniform glow across the night sky. Initially, it was dismissed as simply background noise, a persistent hum of energy. However, persistent observations by several teams, notably Arno Penzias and Robert Wilson in 1964, revealed something far more extraordinary. This noise was remarkably consistent in all directions, and it had a specific temperature, a frigid 2.7 Kelvin, or minus 270.45 degrees Celsius. This wasn't random static. It possessed a pattern, a subtle texture that hinted at an incredible story. The CMB isn't a light source in the traditional sense. It's not radiating energy from a star or a galaxy. Instead, it's the remnant heat from the very earliest moments of the universe. Think of it like this. When the Big Bang occurred, the universe was incredibly hot and dense, a state of plasma where photons, particles of light, constantly bounced off of charged particles. These photons were trapped in a perpetual, chaotic dance, unable to travel very far. The universe was opaque, like a thick fog. As the universe expanded, it also cooled. This cooling process wasn't instantaneous. It happened over hundreds of thousands of years. As the universe continued to expand, it eventually reached a point where the temperature dropped enough for photons to travel freely. Around 380,000 years after the Big Bang, this critical transition occurred, a period cosmologists call recombination. Suddenly, photons were able to stream across space without being constantly scattered. This moment is the key to understanding the CMB. These photons, released during recombination, were essentially the first light of the universe. They've been traveling almost unimpeded for 13.8 billion years, constantly stretching along with the expansion of space. Because space has expanded so dramatically during this time, the wavelengths of these photons have been stretched, redshifted, into the microwave portion of the electromagnetic spectrum. This is why we observe them as microwaves today. The CMB isn't perfectly uniform, though. Tiny fluctuations in its temperature, variations of just a few parts per million, were imprinted during the epoch of recombination. These fluctuations represent density variations in the early universe, slight overdensities of matter compared to the surrounding space. These variations weren't random. They were seeded by quantum fluctuation that existed in the extremely hot, dense conditions immediately after the Big Bang. These density variations acted as gravitational seeds. Over immense stretches of time, gravity amplified these subtle differences, causing matter to clump together to form the structures we observe today. Galaxies, clusters of galaxies, and the large-scale structure of the universe. The CMB, therefore, is a record of the initial conditions that ultimately led to the formation of all these cosmic structures. It's like a fossil, preserving a snapshot of the universe's infancy. Scientists meticulously map the CMB using telescopes on Earth and in space, like the Planck satellite. By analyzing the tiny temperature variations, the anisotropies, we can learn an incredible amount about the early universe. These maps reveal information about the universe's geometry. Whether it is flat, curved, or something in between, its composition, the proportions of matter and energy, and even the distribution of dark matter, a mysterious substance that makes up a large portion of the universe's mass but doesn't interact with light. The patterns within the CMB provide strong evidence supporting the Big Bang theory and offer a detailed picture of the universe's evolution. It's a remarkably accurate cosmological probe, offering far more detailed information than we could possibly gather through observations of the present-day universe. The CMB isn't just a faint glow. It's a treasure trove of information, a tangible link to the very beginnings of everything we see around us. Furthermore, the CMB isn't just a historical record. It's still evolving. As the universe continues to expand, the CMB is redshifted even further, meaning its temperature is decreasing. Scientists continue to study it, hoping to gain even more insights into the fundamental nature of space, time, and the universe itself. It's a constant reminder of the dynamism and ongoing evolution of the cosmos, and a testament to the power of observation and scientific inquiry. The study of the cosmic microwave background radiation is a truly remarkable achievement in scientific exploration, providing us with a unique window into the birth of the universe and laying the foundation for our understanding of the grand cosmic drama that continues to unfold around us. The vastness of space is a place of subtle wonders, a stage where gravity doesn't just pull things together, it sculpts the very fabric of light. We've journeyed across immense distances, observed the relentless expansion, and understood the faint echo of creation. But there's a trick, a beautiful and profound effect that allows us to see things far beyond what our instruments alone could detect, a process we call gravitational lensing. It's like the universe is playing a cosmic game of hide-and-seek with light, and we're learning how to find the hidden objects. At the heart of gravitational lensing lies Albert Einstein's theory of general relativity. This theory, published in 1915, revolutionized our understanding of gravity. It wasn't simply a force, like Newton described, pulling objects towards each other. Instead, gravity is a consequence of space and time being warped by mass and energy. Massive objects like galaxies or even individual black holes create a curvature in space-time around them. Think of it not as a pull, but as a distortion of the path something travels. Now let's consider a massive galaxy, perhaps 1 billion of light years away. Its immense gravity acts like a giant lens, bending the light coming from objects even further behind it. Imagine shining a flashlight at a smooth surface. The light will pass straight through. But if you shine the light at an angle to the surface, the light will be bent as it passes by. The more massive the surface, the greater the bending. It's the same principle, but on a cosmic scale. This isn't just a minor bending. The warping of space-time is so extreme that light from distant galaxies, which would normally pass straight through space, is significantly deflected. These distant galaxies aren't simply appearing brighter, though they often do, they are appearing distorted. Their images can be stretched into arcs, rings, or even multiple images, all because the light has been bent around the foreground galaxy. The most dramatic examples of gravitational lensing are known as Einstein rings. If a background galaxy happens to be perfectly aligned behind a massive foreground galaxy, the light from the background galaxy can be bent around the entire foreground galaxy, creating a complete ring of light. It's a truly spectacular sight, a direct consequence of Einstein's theory and the immense power of gravity. These rings are incredibly rare, requiring precise alignment, but they offer some of the clearest views of the most distant galaxies ever observed. But it's not just about creating perfect rings. Often, the lensing effect produces multiple images of the same background galaxy. This happens when the light from the background galaxy passes close to the foreground galaxy and is bent in multiple directions. These multiple images can be incredibly useful for studying the properties of the distant galaxy, its size, shape, and even the distribution of its stars. Furthermore, gravitational lensing doesn't just reveal distant galaxies. It allows us to probe the mass distribution of the lensing galaxy itself. The amount of bending that occurs depends on the mass and distribution of mass within the foreground galaxy. By carefully analyzing the distorted images, astronomers can map out the dark matter content of the lensing galaxy. that invisible substance that makes up a significant portion of its mass and exerts a gravitational influence. This has become a crucial tool for studying dark matter, providing a way to see it indirectly through its gravitational effects. The process also offers a way to measure the distances to incredibly faint and distant galaxies, galaxies so far away that their light has been stretched to longer wavelengths, a phenomenon known as redshift. The degree of distortion caused by lensing can be used to precisely determine the redshift, and therefore the distance, to these galaxies. This is particularly valuable because measuring distances in the distant universe is incredibly challenging, and gravitational lensing provides an independent confirmation of our distance estimates. Sophisticated telescopes like the Hubble Space Telescope and the James Webb Space Telescope are specifically designed to exploit this effect. These telescopes can detect the subtle distortions in the light from distant galaxies, allowing astronomers to study them in unprecedented detail. The James Webb Space Telescope, with its powerful infrared capabilities, is particularly well suited for studying the effects of gravitational lensing, as many distant galaxies emit light primarily in the infrared part of the spectrum. The research using gravitational lensing isn't just about observation. It's also about pushing the boundaries of our understanding of the universe. By studying the properties of lensed galaxies, we can test the predictions of general relativity in extreme environments where the effects of gravity are most pronounced. It's a powerful tool for validating Einstein's theories and for refining our models of the universe. Moreover, gravitational lensing is opening up new avenues for discovering and studying exoplanets, planets orbiting stars beyond our own solar system. When a massive galaxy acts as a lens, it can magnify the light from a smaller planet orbiting a star behind it, making the planet appear brighter and larger than it would otherwise. This effect, called microlensing, provides a valuable method for detecting these elusive worlds, especially those that are far too small or faint to be detected by other means. As technology continues to advance, gravitational lensing is expected to play an increasingly important role in our exploration of the cosmos. Future telescopes, equipped with even greater sensitivity and resolution, will undoubtedly reveal even more spectacular and informative gravitational lenses, offering us a deeper glimpse into the distant universe and its hidden treasures. It's a testament to the elegant and profound connection between gravity, light, and our quest to understand the origins and evolution of the universe. It's a truly remarkable effect, a cosmic trick that allows us to peer across vast distances and unlock the secrets of the most distant galaxies. The universe isn't just filled with enormous spiral galaxies like our Milky Way, grand and swirling islands of billions of stars. It's also teeming with something much smaller, much more delicate, and frankly, a bit more mysterious: dwarf galaxies. These tiny galaxies are some of the most common objects in the cosmos, representing the vast majority of the galaxy population. They are incredibly faint, often appearing as mere smudges of light even through the most powerful telescopes. Their low mass means they are incredibly susceptible to disruption, a characteristic that has puzzled and fascinated astronomers for decades. These dwarf galaxies weren't always tiny. Billions of years ago, shortly after the Big Bang, they were considerably larger, possibly even resembling miniature versions of spiral galaxies. However, over cosmic timescales, they've steadily lost their stars, primarily through a process called tidal stripping. This stripping isn't a sudden, violent event. It's a slow, relentless erosion caused by the gravitational interaction with their larger neighbors, primarily larger galaxies like the Milky Way. As a dwarf galaxy ventures too close to a larger galaxy, the immense gravitational forces begin to pull at the outer regions of the dwarf. This isn't a direct snatching. Instead, the larger galaxy's gravity creates enormous tidal forces. These forces distort the dwarf's shape, stretching it into a long, tail-like structure known as a tidal tail. This tail isn't made of stars in the traditional sense. It's composed of stars that have been ripped from the dwarf's disk and flung outwards, extending far beyond the dwarf's original boundaries. The exact mechanisms driving tidal stripping are still being researched, but scientists believe that the hot gas within the dwarf galaxy is the primary target. The gravitational pull of the larger galaxy disrupts the dwarf's internal pressure, causing the hot gas to stream outwards along the tidal tails. This gas isn't simply expelled. It's channeled and shaped by the gravitational field, forming intricate, often beautiful structures. The shapes of these tidal tails are incredibly informative, allowing astronomers to map the gravitational field of the larger galaxy involved. There are several distinct types of dwarf galaxies, each with its own unique characteristics and evolutionary history. The most common type is the dwarf spheroidal galaxy. These are roughly spherical collections of stars, typically containing only a few hundred to a few thousand stars. They appear remarkably dark and diffuse, often lacking any discernible spiral arms or disk structure. Their low luminosity and small size make them incredibly difficult to detect, requiring deep observations and careful analysis. Many of these galaxies are located in the outskirts of larger galaxies, where the tidal forces are strongest. Another type, the dwarf irregular galaxies, have a more chaotic appearance. These galaxies lack a well-defined shape and often possess significant amounts of gas and dust. They are frequently found in dense clusters of galaxies, where interactions with other galaxies are more frequent, leading to increased star formation. The intense gravitational interactions trigger bursts of star formation as gas clouds collapse under their own gravity, forming new generations of stars. Then there are the blue compact dwarf galaxies. These are smaller, younger galaxies that are actively undergoing star formation. They are characterized by a blue color, indicative of young, hot, massive stars. These galaxies are often found in relatively isolated environments, allowing them to retain their gas and dust and continue to build up their stellar population. Understanding dwarf galaxies offers a crucial window into the early universe. Because they haven't been subjected to the same level of disruption as larger galaxies, they retain a more pristine record of the conditions that existed shortly after the Big Bang. By studying their stellar populations, the ages and compositions of their stars, astronomers can gain insights into the processes that shaped the first galaxies. Furthermore, the study of dwarf galaxies is helping to address a fundamental question in cosmology. What role did dark matter play in the formation of the first galaxies? Dark matter, an invisible substance that makes up a significant portion of the universe's mass, is thought to have provided the gravitational scaffolding around which galaxies formed. Dwarf galaxies, being small and relatively dark, are particularly sensitive to the distribution of dark matter in their vicinity. The search for faint dwarf galaxies is a challenging endeavor. It requires long exposure times, extremely sensitive telescopes, and sophisticated data analysis techniques. Astronomers use various methods to detect these galaxies, including deep imaging surveys, spectroscopic observations, and gravitational lensing studies. One exciting development is the discovery of ultra-faint dwarf galaxies. These are exceptionally faint galaxies, containing only a handful of stars, sometimes as few as 5 or 6. Some of these ultra-faint galaxies appear to be composed almost entirely of dark matter, offering unprecedented opportunities to study the properties of this elusive substance. The fate of dwarf galaxies is ultimately determined by their interactions with the surrounding universe. As they continue to interact with larger galaxies, they will gradually lose their stars, their shapes will distort, and eventually they will disappear entirely. However, their story, a story of cosmic evolution, gravitational interactions, and the delicate balance between matter and dark matter, continues to unfold, offering valuable insights into the workings of the universe. It's a quiet, subtle process, but a profoundly important one. And as we continue to explore the cosmos, we'll undoubtedly uncover even more secrets hidden within these tiny, fragile galaxies, remnants of the universe's early days, patiently waiting to be discovered. The universe, as we've begun to understand it, isn't simply expanding. It's expanding at an ever-increasing rate. For decades, astronomers had expected that the expansion initiated by the Big Bang would be slowing down. Gravity, the fundamental force of attraction between all matter, should have been acting like a brake, gradually reducing the speed at which galaxies were receding from one another. Edwin Hubble, a brilliant observer of the 1920s, famously demonstrated this initial slowing effect, meticulously measuring the redshift of galaxies, a phenomenon where light stretches towards the red end of the spectrum as objects move away from us. This redshift was directly proportional to distance, suggesting a universe expanding uniformly and, crucially, slowing down with time. The prevailing model was remarkably elegant, built upon a deep understanding of gravity and its effects. However, in the late 1990s, everything changed. Two independent teams of astronomers, using the Hubble Space Telescope, were tasked with measuring the distances to distant supernovae, incredibly bright stars that briefly outshine entire galaxies. These supernovae served as standard candles, objects with known intrinsic brightness. By comparing their intrinsic brightness with their observed brightness, scientists could calculate their distance. The results were astonishing. The supernovae weren't just receding, They were moving away from us faster than expected, based on the amount of matter in the universe. It was as if an unseen force was pushing them apart with increasing strength. The implications were profound. The universe wasn't slowing down, it was accelerating. This discovery sent ripples of confusion and excitement throughout the scientific community. It meant that the dominant force in the universe wasn't gravity, as previously assumed, but something else entirely. To explain this accelerated expansion, physicists proposed the existence of a mysterious entity they called dark energy. Dark energy isn't a substance like matter or radiation. It's a property of space itself. Think of it like this. As the universe expands, the volume of space increases. And because dark energy is inherent in space, the amount of space available for it to act upon also increases. This increased space then allows dark energy to exert an even greater outward pressure, pushing galaxies further apart at an ever-increasing rate. It's not a force pushing outwards in the traditional sense. It's more akin to the geometry of space itself, becoming increasingly repulsive. The nature of dark energy remains one of the biggest unsolved mysteries in cosmology. We know it makes up approximately 68% of the universe's total energy density, yet we have almost no idea what it is. There are several theoretical explanations, but none are definitively proven. One leading candidate is the cosmological constant, originally proposed by Einstein himself, who later abandoned it as a paradox. The cosmological constant represents a constant energy density inherent in space, a kind of vacuum energy. It's a simple idea, but the observed value of the cosmological constant is vastly larger than theoretical predictions based on quantum mechanics. Another possibility is quintessence, a dynamic, time-varying field that permeates space. Unlike the cosmological constant, quintessence could change over time, meaning its density and pressure would also change. This would lead to a variable rate of expansion, rather than a constant one. Models involving quintessence often require introducing new fundamental fields and particles, adding even greater complexity to the picture. Another, more radical theory suggests that our understanding of gravity itself is incomplete. Perhaps Einstein's theory of general relativity, which describes gravity as the curvature of spacetime, needs modification on very large scales. Theories like modified Newtonian dynamics, MOND, attempt to explain galactic rotation curves, the speeds at which stars orbit their galaxies, without invoking dark matter. While MOND doesn't directly address the accelerated expansion, some variations attempt to incorporate it into a revised gravitational framework. It's important to note that the evidence for dark energy is overwhelmingly strong. Not only do observations of distant supernovae confirm the accelerated expansion, but measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, also provide independent support. These measurements indicate that the universe is remarkably flat, meaning its overall geometry is Euclidean, like a flat sheet. A universe that is not flat would either collapse under its own gravity or expand forever. A flat universe requires a specific energy density, and the observed amount of matter and energy combined with dark energy perfectly matches this requirement. The ongoing research into dark energy involves a combination of observational and theoretical efforts. Astronomers are conducting deep field surveys, mapping the distribution of galaxies over vast stretches of the sky. They are also searching for phantom energy, a hypothetical form of dark energy with an even more negative pressure than quintessence, which could lead to an even faster and more dramatic acceleration. Scientists are meticulously refining measurements of the Hubble constant, the rate at which the universe is expanding, and exploring alternative models of gravity. Ultimately, understanding dark energy is key to unlocking the ultimate fate of the universe. Will the acceleration continue indefinitely, leading to a big rip, where all matter is eventually torn apart? Or will the expansion slow down, eventually leading to a big crunch? The answer, we believe, lies in the deeper secrets of this elusive force, a force that dominates the cosmos and shapes the very destiny of everything we know. The universe, as we've come to understand it, isn't just a vast, empty space dotted with galaxies. It's a dynamic, evolving place, a cosmic kitchen where elements are constantly being created and spread. The light from distant galaxies, reaching us across billions of years, carries clues about this ongoing process, specifically clues about their metallicity. Metallicity, you see, isn't about how shiny a star is, although the term might suggest otherwise. It's a measure of how much heavier than hydrogen elements a galaxy contains. These heavier elements, forged in the hearts of stars and scattered across space during supernova explosions, are crucial to the formation of planets and, eventually, life. Early galaxies, formed shortly after the Big Bang, were remarkably pristine. They were primarily composed of hydrogen and helium, the very first ingredients of the universe. These early galaxies, often referred to as population III stars, were incredibly hot and massive, burning through their fuel at an astonishing rate. These stars didn't have any heavier elements to burn. They were the raw materials, pure and simple. When these massive population III stars finally died, they didn't produce anything new. They simply released all the hydrogen and helium they'd accumulated into the surrounding space. The light from these early galaxies, while still incredibly bright, was predominantly red, a consequence of the abundance of hydrogen absorbing blue light. However, as time went on, something remarkable began to happen. These first stars seeded the universe with tiny amounts of heavier elements. These elements, mostly carbon, oxygen, and nitrogen, were created in the cores of stars during their lifetimes. When these stars reached the end of their lives and exploded as supernovae, they scattered these elements across enormous distances. This material then became incorporated into subsequent generations of stars, what we call population II and population I stars. The crucial thing is that not all galaxies were equally affected. Some galaxies, like our own Milky Way, experienced a more intense burst of star formation early in their history, leading to a higher overall metallicity. Other galaxies, particularly smaller ones, had a more restricted supply of this enriched material, resulting in a lower metallicity. This difference in metallicity manifests as a metallicity gradient, a gradual change in the abundance of heavier elements as you move outwards from the center of a galaxy. Scientists study this gradient by analyzing the spectra of light emitted by distant galaxies. A spectrum is like a fingerprint of the light, revealing which elements are present and in what amounts. By carefully examining the absorption lines in these spectra, astronomers can determine the metallicity at different distances from the galaxy's core. The further out you look, the lower the metallicity generally becomes. This isn't a perfectly smooth gradient, of course. There are regions where the metallicity might increase due to tidal interactions with other galaxies, or the formation of denser clumps of stars. The shape and steepness of the metallicity gradient provide valuable information about the galaxy's formation history. A steep gradient suggests a relatively rapid burst of star formation early on, while a shallower gradient indicates a more gradual, prolonged process. Furthermore, the specific types of heavier elements observed can also tell us about the types of stars that were prevalent in the galaxy's past. For instance, a high abundance of oxygen could point to a history dominated by massive, short-lived population II stars. Interestingly, dwarf galaxies often show particularly pronounced metallicity gradients. These smaller galaxies, frequently found orbiting larger galaxies like our Milky Way, tend to be more isolated and have had less opportunity to interact with and incorporate material from other galaxies. Their limited access to fresh, enriched material contributes to their lower overall metallicity and a more pronounced gradient. Studying these gradients in dwarf galaxies provides a valuable laboratory for testing models of galaxy formation and evolution. The chemical evolution of a galaxy is therefore intricately linked to its star formation history. Each generation of stars, born from gas that has already been enriched with heavier elements, contributes to the next generation's chemical makeup. This process repeats itself over billions of years, gradually transforming the galaxy's elemental composition. It's a remarkably efficient recycling system, utilizing the products of stellar death to fuel the birth of new stars and planets. Furthermore, the metallicity gradient isn't just a passive reflection of star formation. It actively influences the formation of molecular clouds, the nurseries where new stars are born. Heavier elements, particularly carbon and oxygen, play a crucial role in the formation of these clouds by providing surfaces for molecules to condense onto. A higher metallicity, therefore, can lead to a greater abundance of molecular clouds, and consequently, a higher rate of star formation. The study of galactic metallicity gradients is a powerful tool in our ongoing quest to understand the origins of the universe and the conditions that led to the formation of our own Milky Way. It's a reminder that galaxies aren't static entities, but are dynamic, evolving systems, shaped by the fundamental processes of star formation and the constant recycling of elements. It's a subtle, almost invisible fingerprint etched across the cosmos, telling a story of billions of years, a story of creation, destruction, and renewal. And like all the best stories, it's still being written. The universe, as we've come to understand it, is a story written in light. Light traveling for billions of years, carrying echoes of events long past, is how we build our knowledge of what came before. For many years, astronomers relied on telescopes like the Hubble Space Telescope to decipher this ancient light. But Hubble, while magnificent, had a limitation. Its vision, primarily in the ultraviolet and visible parts of the electromagnetic spectrum, struggled to see through the dust and gas that often obscured the earliest galaxies. These early galaxies were shrouded, like ancient ruins hidden beneath layers of Earth. Then something truly remarkable happened. In December 2021, the James Webb Space Telescope, or JWST for short, blinked into existence. It wasn't just another telescope. It was a revolutionary instrument designed specifically to peer back further into the universe than anything we'd ever seen. JWST's primary goal was to observe the very first galaxies that formed after the Big Bang, a period shrouded in darkness and mystery. It achieves this by utilizing infrared light. Infrared light, unlike visible light, can penetrate the cosmic fog. Dust, made of tiny particles of gas and rock, readily absorbs visible light, scattering it in all directions. However, infrared light, a longer wavelength, simply passes through these dusty clouds with relative ease. JWST's enormous primary mirror, spanning 6.5 meters across, is crucial to its success. Its size allows it to collect a tremendous amount of infrared light, making it incredibly sensitive. Think of it like a giant ear, designed to pick up the faintest whispers from the distant past. The telescope's instruments, called near-infrared cameras and spectrometers, NIRCam and NIRSpec respectively, are specifically built to analyze this collected light, revealing detailed information about the galaxy's composition, temperature, and redshift, a measurement of how much the light has been stretched by the expansion of the universe. Redshift is intimately connected to distance. The higher the redshift, the further away and earlier in time the light originated. Early observations with JWST have already dramatically changed our understanding of the universe's infancy. Before JWST, we had only theoretical models of the earliest galaxies, based on simulations and limited observations. Now, we're seeing those models challenged, and in some cases, completely overturned. One of the most exciting discoveries has been the prevalence of surprisingly bright, massive galaxies existing just a few 100 million years after the Big Bang. These weren't the small, dim, chaotic clumps of stars that astronomers had anticipated. Instead, JWST has revealed galaxies that are considerably more evolved and complex, possessing structures resembling spiral arms and even evidence of ongoing star formation. The key to understanding these unexpected findings lies in how JWST's infrared vision can see through the dust. It turns out that the dust, which we previously thought was a major impediment to observing these early galaxies, might actually have played a crucial role. Some theories suggest that the dust acted as a lens, magnifying the light from these galaxies and making them appear brighter and more defined than they otherwise would. This magnification effect, combined with the sheer sensitivity of JWST, has allowed astronomers to observe galaxies that would have remained invisible to previous generations of telescopes. Furthermore, JWST's spectroscopic data, essentially a detailed analysis of the light's different wavelengths, is providing unprecedented insights into the composition of these early galaxies. The team is analyzing the spectral signatures of elements like oxygen and carbon, which tell them about the processes occurring within these galaxies. The presence of heavier elements heavier than hydrogen and helium, at such an early stage of the universe's history, was a significant surprise. These elements are forged in the hearts of massive stars and released back into the interstellar medium through supernova explosions. The observations are also revealing a more complicated picture of galaxy evolution than previously imagined. It appears that galaxies weren't simply forming gradually, one after another. Instead, there was a period of rapid assembly, with smaller galaxies merging together to create larger, more complex structures much faster than anticipated. JWST is effectively capturing these moments of galactic collisions and mergers, providing a direct visual record of this chaotic process. The team is looking for evidence of tidal streams, the disrupted remnants of galaxies caught in the gravitational embrace of a merging galaxy. JWST is not just observing the first galaxies, it's also providing a new framework for understanding the universe's timeline. By studying the properties of these early galaxies, astronomers can refine their models of how the universe evolved over time, from the Big Bang to the present day. It's a continuous process of observation, analysis, and revision. As JWST continues its mission, it's expected to uncover even more surprises, rewriting our textbooks and forever changing our understanding of the cosmos. The telescope's lifespan is planned to be extensive, with numerous instruments planned for future upgrades and experiments. Each observation is a precious opportunity to unravel the secrets held within the ancient light, bringing us closer to understanding the very origins of everything we see today. The echoes of the Big Bang are being heard, and JWST is the instrument that is finally allowing us to decipher their message. The spiral arms of the Milky Way, a breathtaking river of stardust stretching billions of light years, aren't just pretty to look at. They tell a story, a surprisingly insistent story about the unseen ingredients that make up most of the universe. For many years, astronomers were puzzled by a peculiar observation regarding our own galaxy, a puzzle that ultimately reshaped our understanding of what the cosmos is truly made of. It began with the study of how stars rotate within the Milky Way. Early measurements of stellar motions relied on observing the light emitted by these stars. As a star moves towards us, its light waves are compressed, shifting towards the blue end of the spectrum, a phenomenon known as blue shift. Conversely, a star moving away from us experiences stretched light waves, shifting towards red, a process called redshift. The amount of this shift directly related to the star's speed. If a star's light is shifted significantly, it's moving very quickly. But when astronomers began meticulously tracking the speeds of stars in the outer regions of the Milky Way, they found something utterly unexpected. The prevailing theory at the time suggested that the speed of a star should decrease with increasing distance from the galactic center, much like the planets in our solar system. The farther a planet is from the sun, the slower it orbits. This is because the gravitational pull of the sun diminishes as you move further out. So, stars at the edges of the galaxy should be orbiting at slower speeds. It was a logical prediction based on Newton's law of universal gravitation, a cornerstone of physics for centuries. However, what the astronomers actually measured was dramatically different. They discovered that the rotational speeds of stars in the outer spiral arms remained remarkably constant, far exceeding what the simple gravitational pull of the visible matter, the stars, gas, and dust, could account for. The further out they looked, the faster the stars were rotating, almost as if they were running on a treadmill set at an incredibly high speed. It's like trying to figure out how much a child is spinning on a merry-go-round based only on the visible children sitting on it. If the child is spinning incredibly fast, you'd realize that there must be something else providing the force pushing them around, perhaps a hidden motor or a strong wind. Similarly, the constant rotational speeds of the outer stars hinted at a significant, unseen influence. The situation was further complicated by observations of galactic rotation curves in other spiral galaxies. Astronomers began to notice that this peculiar phenomenon wasn't unique to the Milky Way. It was a common characteristic of spiral galaxies observed across vast distances. This suggested that the problem wasn't a quirk of our own galaxy, but a fundamental property of spiral galaxies in general. The most compelling explanation emerged from the work of Fritz Zwicky, a brilliant but often overlooked scientist who studied the Coma cluster of galaxies in the 1930s. He noticed that the galaxies within the cluster were moving much faster than expected based solely on the visible mass of the galaxies themselves. He hypothesized that there must be a substantial amount of missing mass, a substance that wasn't emitting light, contributing to the gravitational force holding the cluster together. He even proposed a name for this elusive substance: dark matter. Zwicky's initial calculations were based on measuring the velocities of galaxies within the cluster, predicting that their speed should decrease with distance from the cluster's center. However, the observed speeds remained constant. This meant that the gravitational force exerted by the cluster was far stronger than could be explained by the visible mass of the galaxies. Zwicky's ideas were initially met with skepticism, but his work laid the groundwork for the eventual acceptance of dark matter. Today, the overwhelming evidence derived from numerous observations of galaxies like the Milky Way and clusters of galaxies points to the existence of dark matter. We don't yet know what dark matter is. It doesn't interact with light, making it invisible to our telescopes. Scientists are actively searching for dark matter particles through various experiments, hoping to directly detect their existence and unravel this cosmic mystery. The constant rotation curves of galaxies, once a perplexing puzzle, now stand as a powerful testament to the hidden architecture of the universe, a universe dominated by a substance we can't see, but whose gravitational influence shapes the very structure of galaxies. It's a reminder that the cosmos is far more complex and intriguing than we might initially perceive. The Milky Way, our vast island universe, isn't an isolated entity. It's constantly being reshaped, constantly influenced by the gravitational tugs of neighboring galaxies. For a long time, astronomers primarily focused on larger, more obvious galactic mergers, the kinds that dramatically alter a galaxy's shape and trigger intense bursts of star formation. However, there's a much more subtle and surprisingly complex player in the galactic drama: the Sagittarius dwarf spheroidal galaxy. This tiny, faint galaxy is currently orbiting our own, and its history is intertwined with the Milky Way's past in a way that's still being meticulously unraveled. The Sagittarius dwarf spheroidal galaxy isn't a particularly spectacular sight. It's incredibly faint, and it's shaped like a distorted, elongated blob. It's incredibly small, only about 10,000 light-years across. That's a tiny fraction of the Milky Way's 100,000 light-year diameter. What's remarkable isn't its size, but its incredibly tangled path around our galaxy. It's not following a simple, predictable orbit like a planet around a sun. Instead, it's been repeatedly disrupted and stretched, appearing in different orientations as it passes through the Milky Way's disk. Its story begins billions of years ago, likely during the early stages of the Milky Way's formation. Astronomers believe Sagittarius was once part of the larger Sagittarius dwarf S galaxy, a group of smaller galaxies that were themselves gravitationally bound. This larger group was itself a satellite galaxy, initially formed from the accretion of smaller clumps of gas and dark matter. This initial group then collided with and merged with the proto-Milky Way. The exact details of this initial merger are still debated, but simulations suggest it happened around 8–10 billion years ago. What happened next was a series of repeated close encounters. As Sagittarius passed through the Milky Way's disk, the gravitational forces exerted by the denser regions of our galaxy, particularly the spiral arms, began to pull it apart. This process, known as tidal disruption, stretched the galaxy into its current distorted shape. Imagine a river flowing around a boulder. The water gets pulled and distorted as it passes. Similarly, Sagittarius is being stretched and stretched by the Milky Way's gravity. Crucially, these encounters aren't just stretching Sagittarius, they're also stripping away its stars. The Milky Way's gravity isn't just pulling on the galaxy itself, it's also pulling on the stars within it. These stars, being relatively loosely bound, are flung outwards, sometimes temporarily becoming part of the Milky Way's disk, before eventually being pulled back in or ejected entirely. This stellar stripping contributes significantly to the galaxy's current appearance and its dwindling mass. The beauty of studying Sagittarius lies in the streams of stars that it's leaving behind. These streams are faint, diffuse regions of stars that are being dragged along with the galaxy as it orbits. Astronomers use telescopes like the Hubble Space Telescope and the James Webb Space Telescope to study these streams, searching for the specific chemical signatures of stars that were once part of Sagittarius. They're looking for variations in the abundance of elements like helium and heavy metals. The Webb telescope's infrared capabilities are particularly valuable in this context. Because the streams are faint and often obscured by dust within the Milky Way, Webb can peer through the dust and directly observe the stars themselves. This allows astronomers to determine their ages and metallicities with greater precision. Analyzing these properties helps them reconstruct the history of Sagittarius and understand how it evolved over billions of years. Interestingly, the streams aren't just one continuous thread. They're fragmented and tangled, reflecting the chaotic nature of the interactions. Some streams are tightly wound, while others are more loosely connected. The way these streams are arranged provides clues about the exact timing and sequence of the encounters between Sagittarius and the Milky Way. Current research suggests that Sagittarius has passed through the Milky Way's disk several times, each time leaving its mark on the galaxy's structure. Furthermore, the study of Sagittarius isn't just about understanding a single galaxy. It's providing valuable insights into the processes of galaxy formation and evolution throughout the universe. The way galaxies interact and merge is a fundamental aspect of how large structures, like galaxies and galaxy clusters, come to be. Sagittarius's history represents a microcosm of these larger processes. Scientists are now attempting to determine whether Sagittarius is destined to be completely consumed by the Milky Way, or whether it will continue to orbit for billions of years to come. It's possible that future encounters will eventually disrupt the galaxy beyond repair. However, the complexity of its orbit and the ongoing observations being conducted with the James Webb Space Telescope are pushing the boundaries of our understanding, offering a remarkable glimpse into the tangled and fascinating history of our galactic neighborhood. The story of Sagittarius is far from complete, and with each new observation, we get closer to unlocking the secrets of this elusive, trailing galaxy. The vastness of the observable universe, as revealed by instruments like the James Webb, paints a picture increasingly dominated by emptiness. Dark energy, the mysterious force accelerating this expansion, isn't just a passive observer. It's actively shaping the destiny of galaxies, and by extension, the future of cosmic structure. Our current understanding suggests that the rate of expansion isn't constant. Instead, it's accelerating, meaning the space between galaxies is growing at an ever-increasing pace. This has profound implications for how galaxies will form and evolve over the next billions, even trillions of years. Initially, the expansion was slow, driven primarily by the gravitational attraction of matter, the combined pull of all the stars, gas, and dust within galaxies and clusters. Gravity, the architect of the early universe, was attempting to slow down this expansion. However, dark energy is winning the battle. It's a repulsive force, acting against gravity on the largest scales. What this means is that galaxies, which were once pulled closer together, are now drifting apart at an ever-increasing rate. The rate of mergers, those grand, chaotic collisions that shaped the early universe, will dramatically decrease. Instead of spectacular galactic clashes, we'll witness a universe where galaxies remain isolated, separated by vast gulfs of space. The density of matter, the very stuff that allows for gravity to work, is gradually diluted by this relentless expansion. Looking far into the future, perhaps 10 billion years from now, the situation will be remarkably different. The observable universe will be a sparsely populated realm. Galaxies, the last bastions of concentrated matter, will be incredibly distant from each other. They will appear as faint, almost ghostly smudges of light, truly isolated islands in a sea of dark energy. Many of the smaller galaxies, like the Sagittarius dwarf spheroidal galaxy we've been studying, will have long since been torn apart by the relentless expansion, their stellar components flung outwards into the vast expanse. The evolution of these remaining galaxies won't cease entirely, of course. Within the galaxies themselves, star formation will continue, though at a greatly reduced rate. As the supply of gas and dust, the raw ingredients for new stars, diminishes due to the expansion and the heat generated by existing stars, the rate of star formation will gradually slow down. Massive stars, brilliant and short-lived, will burn out first, followed by the less luminous but much longer-lived main sequence stars. Interestingly, simulations suggest that even in this dark energy-dominated universe, some mergers will still occur, albeit on a much smaller scale. These mergers will be driven not by the gravitational attraction of entire galaxies, but by the tidal forces exerted by smaller dwarf galaxies on larger ones. The larger galaxies, weakened by the ongoing expansion, will be more vulnerable to these disruptive tidal forces. These smaller, disruptive mergers won't create spectacular galactic collisions like we might imagine, but rather a slow, persistent process of stellar cannibalism, stripping stars from the outer regions of galaxies and feeding them into the central cores. The nature of dark energy itself remains a profound puzzle. We know it's responsible for the accelerating expansion, but we don't know why it exists or what its fundamental properties are. There are various theories, from a cosmological constant, a constant energy density permeating all of space, to more complex models involving quintessence, a dynamic energy field whose density changes over time. Regardless of the answer, the continued existence of dark energy dictates the ultimate fate of the universe and shapes the evolution of galaxies. Looking even further into the future, perhaps 1 trillion years, the situation becomes increasingly speculative. As the universe continues to expand and cool, the density of matter will become so dilute that the universe will essentially become a vast, cold void. The last stars will have long since burned out, and the faint echoes of their light will fade away. The galaxies themselves, now just distant, faint remnants, will be almost impossible to detect. The universe, in this far-flung future, will be characterized by its emptiness, a testament to the dominance of dark energy. It's a sobering thought, perhaps, but also a beautiful one. The universe, despite its violent beginnings and its eventual fate, is a dynamic, evolving system, shaped by forces we are only beginning to understand. The future of galaxy formation and evolution in this dark energy universe is one of isolation, decay, and ultimately, a return to a state of almost complete emptiness. And yet, within that emptiness, the faint remnants of galaxies will continue to shine, a silent witness to the incredible journey of the cosmos. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. The vastness of galaxies has now faded, swirling like distant stardust. Let your thoughts drift, calm and unhurried, like cosmic clouds across an endless expanse.